Welcome back, everyone. This time we'll talk about measures of position. We've already talked about the frequency distributions, many graphs and displays, central tendency, remember? Mean, median, mode, range, measures of variation like range, standard deviation, variance, and now we'll talk about measures of position. We're going to talk about quartiles. Of course, you're familiar with quarts, right? We're going to talk about the interquartile range, which can be handy in a couple of different ways. How to create a box and whisker plot, a real simple one. Anyone can do this. Almost anyone anyway. How do you interpret them? Fractals. Don't get scared about that. They are just quartiles, deciles, and percentiles. It's how you take your ordered data and chop them up into sections. And last of all, we'll talk about z-scores, and that might be the easiest part. No, can't be. It's all easy. Just get a little bit of practice. All right. Mentioned fractals just a minute ago. And that just is a generic term for splitting or partitioning ordered data into equal parts. Those are the important things. Quartiles, quart, 4 quarts in a gallon. That means we'll split the data into 4 equal parts. Quartile 1 means a quarter of the data is on or below. Second quartile, half of the data is on or below, also called the median. And third quartile, 3/4 of the data fall on or below, Q3. We need some examples to play with, right? So you get accustomed to what these things really represent. Well, first of all, do you remember what I mentioned should be done first? If you said sort it, yes. The solution doesn't mention that you can't find Q2 or Q1 or Q3 unless they're in sorted form. So there's our data sorted. And the median right here, right in the middle. It splits the data into halves. Q1 splits the first half of the data into halves. In other words, quarters. And Q3 splits the upper half of the data into fourths. Hence, Q, quartiles. Q1, Q3, and of course Q2, also known as the median. So if you look at the data back here, slip back again, see the numbers. Let's get rid of those markings for you. There you go, that looks better. So you can see the actual data themselves. And you can tell from that, well, you can read this for yourself. Just the first one, auto commuters waste 1/4 of the commuters waste 26 gallons of fuel or less. 31 gallons or less, half of them do that. 35 or less, 75% do that. Now we'll switch to tuition costs. We've got 25 liberal arts colleges. It's our N, small n. We're assuming this is probably a sample. And what do you notice? Well, first of all, I notice they're not in order. But if you grab your TI-84, you can put those in order real fast. In fact, not only that, but your calculator, if you ask it for one variable statistics, is going to give you all those quartiles. It'll give you the minimum, Q1, Q2, Q3, and the maximum with almost no effort. The hardest part really is making sure you get all these numbers in correctly. It's a good idea to put those in and have one of your friends or relatives or something check to see if those numbers are correct before you try to ask the calculator to go to work for you. So if you do that, and that's good practice for you, you should find shows Q1, Q2, and Q3, as well as the minimum and maximum, but those are the quartiles. 3 different ways you could do that. Now, we definitely do not use StatCrunch. In fact, I've never used StatCrunch. That doesn't mean anything about StatCrunch, it just means I haven't. Minitab I actually used for a class once, about 10 years ago. And if you should ever need to use Minitab, fear not. If you can do these things on the TI-84 Plus, this is not hard to learn. It's just different. That's all there is to it. And this is what you're going to be probably using, unless you've got a TI Inspire. And then it might almost be easier. If you wonder how to do it on the TI Inspire and you've got one of those, just ask me in class or send me an email message. I can probably tell you the steps. Okay, so here are some summaries you can get just by looking at these numbers right here. I guess I missed max. There we go. All right, next, the interquartile range. Well, of course, you have to know what the quartiles are to get the interquartile range. How do you do that? The difference between the third and first quartiles. Very simple. Difference, what's that mean? It means you're going to subtract. Should be a U here. And this is how you do it. Q3 minus Q1. You found these in your calculator. Just subtract those 2 values. You've got your interquartile range. And that's going to be handy, as you see in a minute. So how do we do that? What do we do with it? Well, usually we use it to identify outliers, really unusual data. Data that maybe you have to take a second look at and make sure it's real data. In other words, that it isn't a mistake of some kind. So, how do you get those outliers identified? First, find the interquartile range. Second, multiply that interquartile range by 1.5. Now that might not run off your tongue real easily. It's not an even number, but remember, interquartile range times 1.5. You're going to use those 2 numbers. Well, actually that number. You're going to use that to create 2 more numbers. First of all, this 1.5 times the interquartile range, you're going to subtract it from Q1. And you're going to add it to Q3. And anything less than Q1 minus 1.5 IQR is an unusual item, an outlier. Anything greater than Q3 plus 1.5 IQR is an outlier as well. In other words, very big or very small. And this is an easy way to tell which items are unusual. So let's go back to the previous example. Are there any outliers? Well, this is our interquartile range. There's Q3 minus Q1. What do we do next? Multiply it by 1.5. And what are we going to do next? We're going to take this 17.25, which is 1.5 times the interquartile range, and we're going to subtract this from Q1, and that'll be our lower boundary, and we'll take Q3 and add this to get our upper boundary. There's our lower boundary. There's 1.5 times our interquartile range. A data entry less than that, because this is the lower bound, anything less than that will be an outlier. We do have one of 19, but Q3 plus that, because 75.25 is the upper boundary, we don't have any up there above 75.75. So we have just one data entry, that's an outlier. Number 19. Remember, that represented 19,000 for tuition. Does that ring a bell? All right. So here's the summary. And notice that this outlier does not affect the interquartile range, because we use Q3 and Q1 to get the interquartile range. But this, the 19, was way outside it, so it doesn't affect finding our interquartile range. Next, the box and whisker plot. Well, you're going to use your calculator and get the 5-number summary. In short, you're going to enter the data, and that's stat edit. Once you've done that, you're going to calculate, and you'll go to stat, calculate, and then you'll use one. The first item on that menu is one variable stats. And that will give you your 5-number summary. Now, if you don't see it right away, and you won't, just arrow down until you get to the bottom, and you'll see the 5-number summary. The minimum, Q1, median, Q3, and maximum. They're all there right at the bottom next to each other. This allows us to easily highlight the important features of the data set with a little bit of a picture. There's our 5-number summary. And this is how you put it together. Make sure that the minimum and maximum are going to fit into your sort of number line down here. Make sure the minimum and maximum fit inside that line. Cover the range of the data. Plot the 5 numbers. There's the minimum. There's Q1, Q2, Q3, and the maximum item. Draw a box from Q1 to Q3. put a vertical line in the box where the median is, and then finish that off by drawing whiskers from the box, the maximum and minimum values. So Q3 to the top, Q1 to the bottom, and you've got your box and whisker plot, and this gives you an idea of what all your data look like when you think of them as a whole. Now why don't you stop the video right here, put pause, and use these 5 numbers and create your own box and whisker plot, and you compare to what you just saw in the last slide. All right, you're back. Is this what you got? I hope. Make sure your number line at the bottom handles 19 and handles 61, lowest and the highest values, and create your box and whisker plot. And you can take a look at these and you can create your own summary, because you know 25% is here, the next 25% is here, the third 25% is here, and the top 25% is there. You can see just by looking at it that this suggests that 19 might be an outlier, and we did show it by using our interquartile range. So, fractals. We've got 3 basic fractals, although you can create any kind of fractals you want. You could divide the data into 5 equal parts if you really wanted to. But we're going to stick with quartiles, 4 equal parts, deciles, 10 equal parts, percentiles, 100 equal parts. How can you interpret that? Well, here's an ogive. Remember the ogive takes cumulative frequencies or relative frequencies, and the question here is, which test score corresponds to the 90th percentile? Actually, this is pretty easy. The percentiles are the vertical axis. So you just go up to the 90th percentile, go across here till it hits the curve. Where does it hit the curve? Just go straight down, and you can see it hits about 1350. So the test score 1350 represents the 90th percentile. What does that mean? It means a person who gets a 1350 has scored higher than 90% of the people that took the College Board test. Now, what if you want to get a percentile for a particular entry? Let's suppose you had a certain SAT score, yours, and you want to change that to the percentile. If you know what the mean and standard deviation are for the SAT, and you know your score, you can find out your percentile, even though it probably will come in the record, but you could do that if you didn't have that. So here's the formula. Remember, this is for data entry X, not for all the data, just one particular data item, and you want the percentile for that one. So you look at X in your ordered list for your data. How many items are less than X? Just count them up. Divide that by how many items of data you have, usually N. Convert that to a percentile by multiplying that fraction by 100, and you got your percentile. Round to the wholest number, nearest whole number, because no one cares about decimal points on that. If you want to use the TI-84, which is a good idea, You can go to second bars, which gets you to the distribution menu. You want to use the second item on that menu, which is called normal CDF. Now make sure you don't pick number 1 by accident. This is the wrong one. It's normal something, but it's PDF. You don't want that one. Make sure you always go to the second item in that menu. How do you figure it out? Well, percentile, remember, refers to all the items that are less than X. So what you want to do is you want to tell normal CDF, okay, start with negative infinity. Get everything to the left. We're going to stop at X. We're going to tell the normal CDF what's the mean of this distribution and what's the standard deviation of this distribution. Take that number that you get, multiply it by 100, and that will give you a percentile when you round it off. So, in the example, how about the 57, which represents 57,000? Well, first of all, how many are less than that? Well, it turns out there are, let's see, I lost track. Oh, I got it. There are 15 less than the 57. So here's our 57. There are 15 items that are less than the 57. There are 25 of these altogether. So you put the 15 on the top, that's how many were less than 57. Total number of data items, 25. Multiply that fraction by 100. This one came out even, but if it doesn't, round it off. And there's your percentile. 57,000 as a tuition corresponds to the 60th percentile. In other words, someone paying a tuition of 57,000 pays more than 60% of the people paying tuition. And now we'll talk about z-scores and how neat they are, really. It sounds like, who cares? Z-score? Sure. Well, it enables us to do some really interesting things. Not only that, that's easy. How do you create the z-score? There you go. Take whatever value you're interested in, just like when we found the percentile. Take that value, that's your x. Subtract the mean from that, that's your mu. Divided by the standard deviation, that's small sigma. That is your z-score. Let's get a little bit of practice here. Get some really simple things. The mean speed, remember that mean speed is mu, is 56 miles per hour along this certain stretch of highway. What you want to do is, if you've found someone who's going at 62 miles per hour, what's the z-score for that particular car? What's the z-score for one that's going 47 miles an hour? And how about 56? Well, you should be able to do that, remember? Small formula, if you want the z-score, take that value, like these here, the 62, 47, and 56. Take that value, subtract the mean, there's your 56 over here. Divide that by the standard deviation, which is right there, and you can get all three of your z-scores. And there they are, 62 minus 56 over the standard deviation. So the z-score for the 62 mile per hour driver is 1.5. Notice it's positive. That means it's 1.5 standard deviations above average. The 47 mile per hour, it's negative, so it's less than the average speed. And you want to remember this one as well, because if this person is going the same thing as the average, the z-score is 0 because there is no difference. It isn't higher or lower than the mean value. By the way, we're going to draw pictures a lot. If you use the bell curve with z-scores, 0 is going to be right in the middle where the mean is. Positive scores out this way, negative scores out that way. Now, you're going to see how we can take things that are not related, not really, and compare them anyway. This is really neat. Most of us know that a 6 foot tall man doesn't look quite as tall, maybe, as a 6 foot tall woman when we put the man with other men and the woman with other women. Well, let's see how different it really is. Does our impression or our idea actually work out number-wise? Let's do it. So what we want to do is first, we want to take the 6 foot tall man, and we're going to use our values down here to find the z-score for a 6 foot man. Well, first of all, because you've got values in inches down here, you need the 6 foot in inches. So for the 6 foot tall man, that's 72 inches. Subtract the mean. The mean down here says 69.9. 69.9. And the standard deviation for the man is 3.0. Now we can get that in a moment. For the woman, again, she's 72 inches tall, but the average woman is 64.3 inches. And the standard deviation is different as well, 2.6. Now let's see how they stack up. 72 inches is what we need. Find the z-score for each one. For the man, you get a z-score of 0.7. Notice that this is a positive one, and that does tell you that the 6 foot tall man, or any 6 foot tall man, is a little bit taller than the mean. Positive means taller than the mean. The 6 foot tall woman, a z-score of 3.0. Positive means that's taller than the typical woman. And remember something else I told you. These z-scores represent standard deviations. So a 6 foot tall man is 0.7 standard deviations above average. The 6 foot tall woman is 3 standard deviations above average. 3 standard deviations? That is really tall. So for the man, it's a typical height. For the woman, that's unusual. And here, last of all, you might want to take a note of this. When you get those z-scores, If you get a z-score within 2 standard deviations, that's rather a usual score. You could see those all the time, or they would happen all the time. If it's between 2 and 3 standard deviations away from the mean, which is z of 0, either here or here, that means they're unusual. Not very strange, but you don't see them that often. If they're above 3 standard deviations in either direction, then they're very unusual. You could go months without seeing someone that tall or that short. Well, I hope you've gained a bit of information here and some skills. Try your exercises, bring those questions to class that you don't have resolved, and we'll take care of those, get you some good answers. In the meantime, you take care and keep smiling. Bye.